Okay, let's get started. Hello, everyone. As I glanced at the list of the participants, we have international audiences. So good morning, good afternoon, and good evening. I hope you have a good day so far. Thank you for joining us. It's my great pleasure to introduce our honorable speaker, Professor Chen. He is an associated professor at Department of Mathematics, National Taiwan University. His research interests are representation theory of Lie algebras and Lie superalgebras, and he will be speaking on Whittaker modules for quasi-reductive Lie superalgebras and principal finite W-superalgebras today. Please start, dear professor.
Thank you very much. I would like to thank very much to Oscar for invitation and for the introduction. In this talk, I will introduce Whittaker modules for quasi-reductive Lie superalgebra and its connection with reputations of principal finite W superalgebras. This is based on joint work with Chen and Volodymyr Marchuk. Okay. It's my great pleasure and honor to give a talk at this the webinar. Here is the outline of my talk. In this talk, I will first introduce simple and standard Whittaker modules, and then we discuss Whittaker modules and the relation with its relation with reputations of principal finite W superalgebras, and we explain a super analog of Segren's structure size. Okay, let's get started. Now, let's set up some notations. We fix a complex finite dimensional reductive Lie algebra G, and then we choose arbitrary neo-radical from arbitrary triangle decomposition. And then maybe I use my pencil to then we choose a neo-radical from a triangle decomposition, and we denote the center by a center of the universal enveloping algebra UG by ZG. Then we follow the definition of McDowell and Mr. to define our Whittaker module. So by which you mean G module is called a Whittaker module if it is finitely generated as a G module and locally finite over UN and the center of UG. So for example, modules in the BGG category O are all Whittaker modules. There are some classical results on Whittaker modules and the module category of the Whittaker module category. The first SL2 example is given by Arnold and Picasso, and then Cosent put their example in a more general context, and later McDowell and Mr. develop a systematic way to construct give a more general construction of simple Whittaker module and study their module category. And Beckerling study the multiplicity of standard Whittaker modules. Now let's explain Arnold and Picasso's example. Before this, we denote the caricature of our neo-radical N. the set of characters on our neo-radical n by Chn. Then for arbitrary character in the Chn, vector V in G module is called a Whittaker module associated to this character theta. If this is definition, if this vector V spans a one-dimensional module given by this character theta as a module. And now we have a easy observation. If M is a simple Whittaker module over G, then G is generated by a Whittaker vector associated to a fixed character theta. The following is SL2 example given by Arnold and Pinkerton. Let's denote the Chevalier generator of SL2 by E, H, and F. Here, Cartan subalgebra is spanned by H, and we choose our neo-radical to be. We choose our neo-radical to be the subspace spanned by E. And the following example depends on two numbers, two data. First, we choose a character of N. And which is non-zero, and then we choose a arbitrary number gamma. Then we can extend the regular H module UH to a SL2 module by the following formula of G action. The first formula describes the action of E on arbitrary polynomial of UH. So here we can see that E acts on a polynomial by multiply a scalar theta E, and we change variable from H to H minus 2. And then we have action of F on a polynomial PH given by this formula. And so as a vector space, this is a regular H module. Now we give the G action, so it is now a G module, SL2 module. G is SL2. It turns out that this module is a non-weight simple Whittaker module over SL2 generated by the Whittaker vector 1, the constant polynomial 1 in UH. So this is the first example of Whittaker module, non-trivial Whittaker module. Quotient generalize this construction to arbitrary reductive Lie algebra. For the recipe for his simple Whittaker module is given by a character of N and a central character of G. Before this, let's denote for arbitrary weight root alpha. Let's denote G alpha. Denote the corresponding root space by G alpha. Then for the construction of cosine simple Whittaker module, we first choose a non-singular character of N, by which we mean it does not vanish on any simple root vector. So this is the condition. and then we choose an arbitrary character of a central character of the reductive Lie algebra Chih. Then we consider ZG UN, the subalgebra generated by ZGen UN. It is actually a tensor product of ZGen UN. Then we can form a one-dimensional module which corresponds to which retreat to a character of central character given by chi lambda and the character of theta. So by which you mean for any x in n, z in the center, x minus theta x and z minus chi lambda z, x on which is 0. Then we induce to be a G module. So it is an induced module. And Cosent prove that these modules YG lambda theta give us a complete list of simple Whittaker modules generated by Whittaker vector associated to this character of neo-radical theta. For example, if we consider SL2, then the module V, which we have just defined, is isomorphic to cosine Whittaker module, and the scalar chi and theta is given by the value of corresponding central character on Casimir element and the neo character. For arbitrary character, we need certain standard Whittaker module to construct simple corresponding simple Whittaker modules. For this, we fix arbitrary character. It can be non-singular in the sense of cosine or not non-singular, just singular arbitrary character set. And then we form a Levi subalgebra, which is generated by Cardan subalgebra and the root vector space G plus minus alpha. Here, alpha is chosen to be simple roots such that theta does not vanish on the corresponding root subspace. So if we restrict to this Levi subalgebra, it turns out to be a non-singular. Sorry, here I should say restrict to the Borel subalgebra of this Levi radical, neo-radical. Then this is a non-singular character of the neo-radical of this Levi. It is a reductive algebra with a non-singular character restricted from theta. So now we can form cosine type simple Whittaker module over this Levi subalgebra LZ. So this is a cosine type cosines simple Whittaker module. But over this Levi subalgebra LZ. and we do parabolic induction to reduce to G module. And we refer this module to as a standard Whittaker module following McDowell. For example, if theta is 0, then here we have we don't have the root subspace G plus minus alpha here, so we have cut-down part only. So now the cut-down, the Levy subalgebra is the Levy subalgebra coincides with cut-down subalgebra, and the parabolic induction. So the parabolic subalgebra is just a Borel subalgebra. So in this case, standard Whittaker modules are Verma module. So if we consider the corresponding for each weight, we consider corresponding standard Whittaker module, then it is just the Verma module of highest weight lambda. So this is another extreme case. Constant discuss non-singular case. By which you mean for any simple alpha, for any simple root vector, for any given, for any simple root alpha, theta does not vanish on the corresponding root vector space. But if theta is 0, then this is constant case. The second case is Verma module case. Then it vanishes on any root. Now, the classification of simple Whittaker module associated to arbitrary character theta is given by McDowell and Chih as follows. For each, so each standard Whittaker module has a simple top, which we denote by lambda theta. Then it turns out that all these, the set of all these simple modules, simple Whittaker modules, is a complete list of simple Whittaker modules generated by Whittaker vectors associated to this theta. Now theta is arbitrary. It's not need to be non-singular. And we true standard Whittaker module and lambda theta and mu theta are isomorphic if only if the top are isomorphic, and if only if the weight lambda and mu lies in the same orbit under the Y group action of the Y group of the Levy subalgebra. Here, W subalgebra theta denotes the Y group of Levy subalgebra rotate. And all these standard Whittaker modules are of finite length. For example, if we choose theta to be 0, then we get then the corresponding simple quotient of Verma module are just a simple Ising module. So this simple Ising module of Ising lambda, and we denote by L lambda. So now, interesting question. Natural question is to determine the composition multiplicity of simple Whittaker module in a standard module. For example, if zeta is 0, this is just the question about multiplicity of Fermat modules, which is determined by Cauchy-Lucid theory.
Sorry, Chih. Can you go back? I missed the definition m lambda Quasi. Okay, show me again.
M lambda Quasi
sorry for that. I missed that part. Yeah.
M lambda theta is standard Whittaker module.
Oh, okay. So it's at the I Quasi simple root. I Quasi simple root is
it is parabolic induction from cosine type Whittaker module.
Okay, you add. Oh, this is in if Quasi is Quasi G alpha is 0.
Quasi now is arbitrary character.
Oh, this is a.
We choose an arbitrary character, and we choose simple roots such that Quasi does not vanish on
Okay. Okay.
Thank you. Thank you for your question. Okay. Now, we go. So it is interesting to determine composition multiplicity of standard Whittaker module. The theta equals to 0, then we get the classical part determined by Cauchy-Lucid theory. And now for this Whittaker developed exact function to reduce the problem of multiplicity of standard Whittaker module to that of Fermat module. So this is reduced to Cauchy-Lucid theory. So let me explain Whittaker's function. So following Whittaker, for any module in this is BGG category O. BGG category. Module in BGG category O, we can define a G module, which we denote by gamma zeta of M. We first consider completion of M, by which we mean completion with respect to the weight space. We just do the product of weight space. Then we it has a natural G module structure. Then we collect all vector M such that for any x in the neo-radical, x minus theta of x activate this vector M neopotently. So we can say this is a subspace of vectors on which x minus theta x act locally neopotently. It turns out that the construction of this new module gives us a function from category O to Whittaker category. O to the category of Whittaker modules. And Beckeling proof of, sorry, I've used the notation N. Let's denote the category of all Whittaker modules by N. Then this functor gives us a functor from O to N, and the Beckeling proof that first this is exact functor, and second it sends Verma module to standard Whittaker module, and send simple high-thread module to 0 over simple Whittaker module. So if we want to calculate the multiplicity of N, we can just locate Verma multiplicity of Verma module and try to delete some delete some lambda, L lambda simple high-thread module of high-thread lambda corresponding to non-L theta anti-dominant weight, and then we can reduce the multiplicity problem to that of multiplicity problem of standard Whittaker module to that of Verma module. So in particular, so this theorem reduce multiplicity problem to Cauchy-Luther theory. So in particular, every Whittaker module is of the form of a form gamma theta of L lambda. Now let's turn to Lie superalgebra part. A Lie superalgebra is a vector superspace G equals to even part G 0 bar and other part G1 bar with a bracket, bilinear bracket, satisfied in the following 3 conditions. The first is the 2 compatible condition, which means if we put Gij in the bracket, Gij bracket is a subspace in Gi plus J for any element in Z2, and we have superscale symmetry condition. Here we if we switch the order of A and B in this formula, we get H sign, and we have a super-Jacobi identity. So in this formula, for classical, for Lie algebra, we don't have a sign, but now we change the order of A and B in the classical formula, so we get a sign determined by the parity of A and B. Here, A, B, C are all homogeneous elements. We are mainly interested in the classical Lie superalgebra from Cauchy's list. We have basic classical type Lie superalgebra, GL, SL, PSL, and OSP, and we have exceptional D2 alpha, G3, and F4, and we have strange Lie superalgebra, peripalytic Lie superalgebra, and clear Lie superalgebra, and all of that are quasi-reductive, by which we mean even part is reductive and other part is semi-simple under joint action of the even part. For quasi-reductive Lie superalgebra, we can define a triangular decomposition. For example, if we consider Lie superalgebra GLMN with the following standard bracket. Bracket xy is defined as xy minus, here we have a sign, yx. Then we have a matrix realization of GLMN as n plus n times n plus n matrix. In this case, we can choose, we can define the standard triangle decomposition, for which the Cartan subalgebra is Cartan subalgebra consists of all diagonal matrices, and we define radical n to be the subalgebra of all strictly upper triangular matrices, and another the opposite radical minus to be extremely lower triangular matrix. For all type 1 Lie superalgebra, including GL, P, and OSP, we have distinguished Borel subalgebra, which is given by even Borel subalgebra plus G1. Here, this is an example. Now for Lie superalgebra, the Whittaker module is can be defined in similar fashion. Finally generated G module is called Whittaker module if the action of UN and the even center, the center of even, the center of universal enveloping algebra of even part are locally finite. So for a Whittaker module, we have 3 conditions: finitely generated, and UN locally finite, and even center locally finite. This is our definition of Whittaker modules. There are some known results and connections. For type 1, we have a classification of simple Whittaker modules. For type 1, we have equivalence between Heisenberg modules. And for type 1, we in my joint work with Professor Chen and Volodymyr Marchuk, we study stratified category structure for Whittaker module category, and we do similar thing for non-type 1 Lie superalgebra. And there are some categorification by Whittaker modules. And also we can apply this theory to finite dimensional representations of the principal of finite W algebra. And recently there is a version of superduality for Whittaker module. And finite W algebra established by Chen and Wei-Chang Wang. And we can also apply Whittaker module to finite supersymmetric W algebra. So there are some known results and connection. And now let's go back to classification of a simple Whittaker module over the superalgebra. So now basic natural equation is to classify all simple Whittaker module over quasi-reductive Lie algebra. So basically we can try to do similar construction similar to and make cosine and Macdowell. So we can define parabolic induction, and then we do parabolic. We construct cosine type Whittaker module. But for superalgebra, if we consider cosine type module, then this is not always simple. So it is not easy to construct a cosine type simple Whittaker module, and then we do parabolic induction, because this is not very easy to even for a non-singular case. But for a simple Whittaker module over G, then we still have the following factor. That's this simple Whittaker module M is generated by a Whittaker vector associated to a character Z. And we can prove that if G is of type 1, either of type 1 over the Levi subalgebra is, sorry, this is originally Levi subalgebra of even parts, but if it is also a Levi subalgebra of the whole superalgebra, either G is type 1 over this condition, then we can do Chih and McDowell's standard Whittaker module, and we take their tops and prove that these tops give us a complete list of all simple Whittaker module. And Beckham's function affords a natural generalization such that for any weight lambda, it sends Wehrmann module to standard Whittaker module and kills some simple high-speed module. And for anti-dominant weight with respect to Levi subalgebra, in this case, it sends simple high-speed module to the corresponding simple Whittaker module. So now the problem of finding the multiplicity of standard Whittaker module reduced to that of Wehrmann modules. This has been given by the work of Chen, Liu, and Wei-Chang. For example, if we consider G12, then it turns out that we have two kinds of standard Whittaker module. The first, the easy case is a so-called typical standard Whittaker module. So by which we mean weight lambda satisfy certain condition, which means it is not zero of polynomial T lambda. Then in this case, the standard Whittaker module is simple. The other complicated case is a typical case, which means if lambda is zero of this polynomial, then the corresponding standard Whittaker module has a non-spatial ES sequence. It has a circle part given by this standard simple Whittaker module, and the top given by this. So if G is either basic, classical, or strange, then if M is a simple Whittaker module, then M is always a quotient of the module in the sense of Berkeley. So here we recall if G is a Lie algebra, then all simple Whittaker module are of the form. But for superalgebra, we don't know. But we can prove that it's a quotient of modules of a form. So it's very natural to ask when the following equation is or conjecture is true. For any theta and lambda is the module of the module in the sense of Berkeley, zero over simple. And we prove that this is true for many cases. The first case is G is type 1, then this is always true. Then if the Levy subalgebra set in G even part is still a Levy subalgebra of G, the whole G, the superalgebra G, then this is also true. For integral weight, this is so true. And for basic classical and lambda is certain strong typical weights in the sense of Gorelick, then this is so true. And for OSP1, 2, this is true. And we don't know when this is true, and we conjecture, we guess this should be true. If this true, then we can classify our simple Whittaker modules in this way. Now let's explain Whittaker modules and the relation between Whittaker modules and representations of finite W algebras. The recipe for finite W algebras is given as follows. We fix reductive Lie algebra G with non-degenerate invariant bilinear form, and we also need a nilpotent element E. And we choose a good Z gradient for this nilpotent E, by which we mean the following three conditions. E is of degree 2, and a joint action of E is injective from GI to GI plus 2. Since E is of a degree 2, so this so its adjoint action is from GI to GI plus 2. And the second condition is that this is injective for any I less than or equal to -1. And third condition is that for other cases, this adjoint action is surjective. And we define a functional chi by put E in the first variable for this bilinear this symmetric bilinear form, and we choose maximal isotropy subspace with respect to the bilinear form chi restrict to the subspace G1 G minus 1 times G minus 1, and we form a nilpotent subalgebra M given by this maximal isotropy subspace plus the direct sum of OGI where I runs over all numbers less than or equal to -2, and we define a character of this nilpotent subalgebra. Okay, this is a little bit complicated, but the following Coulson-Leach and Primate, we define finite W algebra associated to G and E as the endomorphism algebra, the opposite of the endomorphism algebra of certain Q theta. This Q theta is the generalized graph module. It is which is defined as induced module from a one-dimensional character of n given by this character theta. So now we have a definition of finite W algebra. It can be proved that because let's go back to the recipe. In the construction, we choose the degenerate binary form and the Z-gradient and the maximum isotropy subspace, and we choose many things, but it turns out that all these choice our construction of finite W algebra is independent of all these choice. It depends on G and E only. For example, if E is 0 element, then G is just a G0 with M equal to 0. And in this case, the finite W algebra is universal enveloping algebra. In another extreme case, if E is principal nilpotent element, by which you mean the adjoint action has dimension, so it should be kernel of adjoint action. We take its dimension is equal to the rank of this reductive Lie algebra. Then in this case, Coulson proved that the corresponding finite W algebra is isomorphic to center. There are some known results given by Primate, Losef, Brandon, Goodwin, Clashman, and others. And they developed a repetition theory of finite W algebra, and we can define Riemann module and corresponding categories of finite W algebra. And for basic for this superalgebra, basic and queer type this superalgebra, there are some results given by Brandon, Brown, Goodwin, and Zhao, and Politava, Skanova, Su, Bing Su, and Yang Zhen, and Bing Su, and Xiao, and Peng, and others. And for peripatetic superalgebra, in my joint work with Chen, we give a construction. And now let's explain Whittaker modules and modules over UGE, the finite W algebra. Suppose G is basic, classical, or strange, and we denote the category denote by C theta the category of all G modules on which X minus theta X locally nilpotently for any X in the algebra M. For each object in this category, we denote by we consider the subspace of Whittaker vectors in this module M. So this means we collect all vector V such that for any vector for any x in M, x V is equal to theta of x V. So this means we collect all the one-dimensional character in this module corresponding to the character theta. And this assignment from C theta to UG module give us equivalence of categories with this tensor function as its quasi-inverse. This is the so-called Scauri-Rabin equivalence, first proved by Scauri-Rabin for reductive Lie algebra, and for basic classical and query superalgebra is proved by Zhao and Su and Xiao. And for type P, we prove the Scauri-Rabin equivalence. So now let's consider the Whittaker category. For recall, we denote by we denote the category of Whittaker modules by N. Then we can decompose into the sum of subcategory N theta. N theta consists of all Whittaker modules such as x minus theta x on which on M locally nilpotently and M is locally finite over the event center. For example, standard Whittaker module and simple Whittaker module are objects on the N theta. If we choose theta to be 0, then this is a sick version of BGG category O. And in Cosen's original paper, he proved that the Scauri-Rabin equivalence retreat to equivalence of category from N theta to module category over finite-dimensional module category over the center in the case when theta is non-singular. So we have an equivalence of categories from Whittaker category and module category of modules of a center. And this can be generalized to basic classical and strange. But now the Scauri-Rabin equivalence retreat to equivalence from Whittaker modules category to module category over of corresponding finite W-superalgebra. In this case, UGE is in general not the center. And for any principal nilpotent element in a Levi subalgebra, and Chen and Wang prove that N theta is equivalent to certain category O of UG module, recovering Loseff's proof of Brandon-Goodwin class-shift conjecture in the setup of reductive Lie algebra. Okay, now let's go to the second functor V. Let G be a reductive Lie algebra. We set lambda to be a anti-dominant weight, and we consider a block containing the corresponding simple isolated module L lambda, and we denote its projective cover by P lambda. The classical Sergen's combinatorial functor V given by Sergen is defined as the following function from category O to ZG mode. This is the module category of center of G. This function is a Hom function. This P lambda is a projective cover of L lambda with the following action of Z. ZF of M is defined as Z, and we first apply F to N, and we multiply it with Z for any F in the resulting module. And circular structure theorem says that V is actually a full and faithful function of projective modules in category O. So it's very useful, and we can transform problems in category O to the corresponding problem in the module category of the center. We know that center are just a polynomial algebra, and there's yet another Whittaker co-invariant function to relate O and finite W algebra. Here we recall if E is non-singular, E is regular, sorry, principal, then by constant this is just principal finite W algebra. So in this case, in the case E is principal, then this is just a ZG module. So like function V and the function H0 has the same codomain. Right now, there is yet another function called Whittaker co-invariant function from category O to ZG mode given by this. Begging proof that in this case, then all these functions and his function are isomorphic up to equivalence between their target categories. And for this superalgebra, we have the following diagram given by Boundary Goodwin. And for this superalgebra of type A, this for the general linear D superalgebra, we consider the integral BGG category O, and we form the cell quotient function from category O to certain cell quotient category, quotient out cell subcategory I generated by O simple Hessian module with non-anti-dominant Hessian. So it's certain cell quotient category with a cell quotient function. Then it turns out that in this case, the Whittaker co-invariant function is isomorphic to the cell quotient function up to isomorphism between their target category. So in particular, the Whittaker co-invariant function is full faithful on projective modules. So it's a version of circular structure theorem. In my joint work, we can generalize to arbitrary type 1D superalgebra. Now for basic classical or strange D superalgebra, the Whittaker co-invariant function, the dual of Whittaker co-invariant function is isomorphic to the composition of backing function and the Whittaker function up to equivalence. But the target category can be non-zero for this superalgebra outside type 1. So we need to change our change the cell subcategory which you quotient out to the cell subcategory generated by a lambda such as P lambda is not injected. So it's just some cell category, and we form the Whittaker category WZ. Then it turns out that we have a version of analog of Bond-Goodwin's result. So we have a commutative diagram from category O to Whittaker category WZ. Then this function of the composition of function, backend function and the Whittaker function is isomorphic to the quotient function, such that it is full festival on projective modules. So use this, we can prove that the Whittaker category WZ has a properly stratified structure, and we can use results structure, use some results about structure on category O to solve problems in the Whittaker category WZ. This category is good because it contains all standard Whittaker modules and all simple Whittaker modules. For example, if we take theta to be 0, then this is just a category O. Now theta can be arbitrary, so it's a variation of category O. Okay. I stop here. Thank you.
Thank you, dear Chen. I really enjoyed. Thank you for the nice presentation and being on time. Yeah. And we will go ahead with questions, comments, suggestions, anything, dear participants.
Okay, how about infinite dimensional Lie algebra like affine Casimir Lie algebras? Is there any kind of similar results?
Thank you. This is a very, very interesting question, but I don't know. I'm not familiar with infinite dimensional, but even for I remember even for category O, it seems even for category O, I'm not very sure we have a nice structure. Sorry, I don't know.
Yeah, there are some results on affine Casimir algebras. So Whittaker modules, the classical Whittaker modules.
Classical. Oh, I see. So you remember you? I remember you have some results for.
Yeah.
All right.
With my co-authors, Rencai, Adamovich, we started. We finished A11 type A11, and then other people they finished all simple list affine Casimir algebras. Yeah.
I see.
For non-simple list affine algebras, we don't know.
As I know, there is no result in the affine super case. I mean,
yeah, you're right.
I couldn't find anything about that, and I asked Chen about this. Did you remember, Chen?
Yes, I remember. But so sorry, I not.
Yeah, I have started to study that topics. Yeah.
Maybe the settings are a little bit different, right?
Yeah, of course. Yeah.
The classical Whittaker modules, well, Yeah, by classical, I mean, what is the guy?
In finite dimension, in
Yeah,
setup of finite dimension,
yeah. Finite
we
Lie algebra. Yeah.
we will first fix the triangle decomposition. So for infinite dimensional, do we do the same thing, or fix a triangle decomposition, and we choose a neo-radical, then we discuss Whittaker modules.
Yeah, I remember, Zhui, you have a paper, say, from highest weight modules, you consider the complication, and then you define Whittaker modules, right?
Right. Highest weight module, right.
For super-algebras, right?
Right. Yeah. Right. Yeah. That's my first paper on Whittaker module.
Okay. Yeah, I'm quite familiar with that one.
Thank you very much for that's
Okay.
interesting, but
No problem. Yeah. I like it. Yeah. It's a different approach.
I say thank you.
Okay, another one. May I please? Maybe it is a silly question. May I please? Dear Chen, can you hear me?
Yes.
I have a question.
Yes. No.
Okay. For a small Lie superalgebra, for example, GL11, is there a complete results that show all representations by your results described by using your results? Is there any complete actually classification for a small Lie superalgebras?
Simple module for
Yeah,
S.
of course. Yeah.
For GL11, I think
For example, for GLL1, yeah.
GL1, simple modules for type for GLMN, I think simple module can be described as simple quotients of Katz module. Katz module is in induction from simple modules of its even parts, and along the type 1 grading. Then I have a joint paper with Mazurchuk. We describe the relation between simple modules of type 1 Lie superalgebra and simple modules of its layer even parts. Maybe I can write something. So if GS GLMM, then we can decompose as 3 parts. This is Z2 compatible Z grading. This consists of matrix, and this is even part. And there's a result saying that there is a 1-to-1, 1-1-2. Sorry, there's a bijection between simple G modules and simple G0 modules, given by Katz induction function, which is defined as induction 0 plus 1 from G0 mode, the module category to category of G0 module to G module, and they will by this we mean K send a simple to simple G0 mode V to the top of the cut module. This gives us a bijection between simple G module and the simple G0 module. So now the question is how to describe the radical part of the KB, the cut function. This called cut function. The top is just defined by quotient out radical parts. There is a unique maximal submodule in KV, and we quotient out, we get a simple module which we call top of this module, and this gives us a bijection between simple G0 module and the simple G module. For we can do the same thing for all any type 1 superalgebra. But there are some beyond type 1 we don't know. Beyond type 1, this is very interesting question. How when we it is interesting to ask when we have a bijection between simple G module and simple G0 module. For beyond type 1, I don't know.
Okay, thanks.
Thanks for your question.
You're welcome. Any other one? Okay, thank you, dear Chen, and
thank you.
Yeah, thank you for accepting my request to talk in our weekly webinar. Thank you so much. And dear participant, I'm so sorry for the delay.
Okay.
Yeah.
Okay.
You're welcome.
Bye-bye.
Bye-bye.
Bye, Saeed.
Bye-bye.
Bye-bye. This is the end of
Bye-bye,
the
Kaiming.
webinar.
Bye-bye.
Very nice.
Very nice to see you. Bye-bye.
You haven't changed any.